Welcome to the second lesson on refrigeration and air conditioning. In the first lesson, we have presented the brief historical aspects of various refrigeration systems. In the present lesson, I will present some historical aspects of refrigerant and compressor development. The specific objectives of this lesson are to outline refrigerant development and various issues related to refrigerant selection and development of different types of compressors. Here the focus is mainly on Vapour Compression Refrigeration Systems, which are the most popular among all the refrigerant systems. And at the end of the lesson, the student should be able to list various refrigerants used before CFCs and their limitations, list various CFCs and their impact on refrigeration and environment, list refrigerants in use after Montreal Protocol, and list various types of compressors and their development. Refrigerant. First of all, let me define refrigerant. A refrigerant is defined as any body or substance that acts as a cooling medium by extracting heat from another body or substance. This is a general definition of refrigerant, and under this broad definition, many substances can be called as refrigerants. For example, if you are using a block of ice for cooling, then the ice can be called as a refrigerant. But since we are interested mainly in closed refrigeration cycles, for us refrigerant means a working fluid that undergoes cyclic changes during the operation of a refrigeration system. So basically we are dealing with working fluids which undergo cyclic changes. Now let us look at importance of refrigerant selection. In the design of any refrigerant system, selection of suitable refrigerant is a very important step, and it is in fact the first step in the design of any refrigerant system. Even though the theoretical efficiency of a Vapour compression refrigerant system depends mainly on the operating temperatures, the selection of a refrigerant decides many other practical issues. For example, the type of the refrigerant used decides the system design aspects, size and weight of the system, initial and operating costs, safety issues, serviceability, and reliability. So you can see that so many practical issues are related to the selection of refrigerant. That is the reason why suitable refrigerant selection is very important. Now let us look at refrigerant development. The development can be divided into three distinct phases. The first phase is the development of early refrigerants, which is prior to CFCs, and the second phase consists of development of chlorofluorocarbon or CFC based refrigerants, and the third phase is refrigerants after Montreal Protocol. Let us look at early refrigerants. As I mentioned in the last class, ethyl ether is the first refrigerant to be used by Jacob Perkins and others in their early refrigeration machines. Ethyl ether was used not because it is an ideal refrigerant, but because it exists as a liquid at ambient conditions. So it is easier to handle. That is the reason why it was used as a refrigerant. But if you remember, I have mentioned that ethyl ether has several problems. For example, if you want to have low temperatures, then your system will be operating under vacuum, and operation under vacuum can lead to leakage of air into the system, which may form explosive mixers with ether. So that is one of the main disadvantages of ether. In addition to that, ether is also toxic. So as a result, people have tried to develop new refrigerants which do not have these shortcomings. So Alexander Twining has proposed the use of ammonia and carbon dioxide as refrigerants in 1850, and ammonia is one of the most important refrigerants because of its excellent thermodynamic properties and its low cost, and also it is easily available. Next, Charles Tellier has tried dimethyl ether in 1864. Dimethyl ether has a low normal boiling point. However, it is also toxic. As a result, that was also not used for a long time. Next, Raoul Pictet has suggested the use of sulfur dioxide. In fact, he has built several systems using sulfur dioxide. Sulfur dioxide is not a inflammable substance. In fact, it is a flame retardant. In addition to that, it also has the advantage that it acts as an auto lubricant. So when you are using sulfur dioxide in a compression system, you do not need any external lubricant. However, the problem with sulfur dioxide is that if in the presence of water, it forms sulfuric acid, and sulfuric acid is highly corrosive, so it can damage the materials of construction. So even though sulfur dioxide was used widely for about 60 years, later it was replaced by other refrigerants. Then Linde has built ammonia systems in 1877. As I said, this is one of the most important landmarks in the history of refrigeration. And Windhausen has used carbon dioxide in 1885. Carbon dioxide, since it is non-toxic and non-flammable, and it's a safe refrigerant, so it was very widely used in marine air conditioning and refrigeration applications. But one problem with carbon dioxide is that it has a low critical temperature, and also its operating pressures are very high. As a result, carbon dioxide was used for about 60 years, and later it was phased out. But again, of late, there is an increasing use of carbon dioxide because of its other excellent properties. Hydrocarbons and their mixers were also tried in domestic refrigerators and other systems. So these are the early refrigerants which were used before the invention of the artificial or synthetic refrigerants. As I mentioned just now, all these earlier refrigerants face from one problem or other. Let's look at these problems. They are some of them are toxic. For example, ether and ammonia are toxic. They had the problem of flammability, particularly with hydrocarbons. Hydrocarbons are highly flammable, so this is one of the problems. And material compatibility. Ammonia is not compatible with copper, brass, etc. So you cannot use these materials when you have ammonia in the system. Then chemical stability, as I mentioned just now, for example, refrigerants like sulfur dioxide react with water and form sulfuric acid. So it is sulfur dioxide is not chemically very stable. And then operating pressures. This is one typical problem with carbon dioxide. Its operating pressures are at least one order of magnitude higher than other refrigerant. That means your system pressures will be very, very high. So you have to design the system to withstand such high pressures. So this is one disadvantage of carbon dioxide. Then limited temperature range. Almost all the refrigerants had a particular temperature range within which they were working, and outside the temperature range they were not good. So these are the typical problems of all the early refrigerants. So as a result, refrigeration industry felt that to make progress, they needed to develop refrigerants that were safe, that were non-toxic, non-flammable, etc. And they felt that because of the safety issues, the growth of refrigeration industry is not as much as it should be. So this led to the invention of CFCs. Thomas Maudsley Jr. and his associates working at Frigidaire Laboratories have been asked to develop new safe working fluids to be used as refrigerants in refrigeration systems. Thomas Maudsley is already famous for his invention of tetraethyl lead, which was an important anti-knock agent. So he has been asked to develop safe refrigerants. So what he has done is he has carried out a systematic study of the periodic table, and he started eliminating the elements which were found to be not volatile, and which were found to be toxic, which were found to be flammable, which were found to be inert. So by this process of elimination, he has finally left with 8 elements. So I'll show you the 8 elements on the periodic table. So you can see the 8 elements which were left out after the elimination process, and I have shown here their atomic number, atomic weight, and the group to which they belong. So you can see here the 8 elements are hydrogen, carbon, nitrogen, oxygen, fluorine, sulfur, chlorine, and bromine, and the colors indicate their condition at room temperature. For example, the green color means that these elements are gases, exist as gases at room temperature, and the red color shows that the element bromine, for example, is a liquid at room temperature, and the pink color, for example, carbon and sulfur, they are solids at room temperatures. So after this systematic elimination and systematic study of periodic table, they have arrived at 3 important conclusions. The first conclusion is that the flammability reduces from left to right. That means the hydrogen is highly flammable, and as you move from the left to right of these 8 elements, the flammability reduces. This is the one important conclusion. And second conclusion is that toxicity reduces as you go from the bottom to top. That means bromine is highly toxic, and the toxicity reduces as you move up. And third conclusion is that all the refrigerants that were available at that time were made out of a few elements of these 8 elements only. That means if you want to make some refrigerant, you have to choose some elements among these 8 only. These are the main conclusions arrived at by Thomas Midgley and his associates. Then what they have done is, after this elimination process and all, they have started developing a series of refrigerants by a partial replacement of hydrogen atoms in hydrocarbons. This is how the CFCs were invented. For example, let me show the this is your typical you have methane atom. Okay, so if you replace this hydrogen atoms, let us say by chlorine and fluorine, I am replacing these hydrogen atoms by 2 chlorine atoms and 2 fluorine atoms. So what we get here is CCl2 F2. So this is one important refrigerant, and it's known as by its number R12. So if you replace, for example, instead of 2 chlorine atoms, for example, I am replacing this chlorine atom with another fluorine atom. So I get what is known as R13. So this is another important refrigerant. For example, again one more 2 more fluorine atoms are replaced by chlorine atoms, let us say. That means we have CCl3F. So this refrigerant is known as R11. So by replacing hydrogen atoms with either chlorine or fluorine, you get a series of different working fluids, and they have shown that by this process you can evolve a large number of refrigerants whose properties are dramatically different from each other, and they have shown how properties like toxicity, flammability, normal boiling point, etc. can be controlled or can be varied by varying the chemical composition. So this is the basis behind the development of several CFCs, and out of this development came the first refrigerant known as Freon 12 or CCl2F2. This is introduced in 1931, and the Freon is the trade name of all the refrigerants manufactured by DuPont Company of USA. And as I said, Freon 12 is the first refrigerant, first CFC refrigerant to be introduced into the market, and it is one of the most important refrigerants, and it was widely used in domestic refrigerators and in small air conditioning systems, etc. Next refrigerant to come out of this is what is known as Freon 11. So it is its chemical composition is CCl3F, and it's normally used for air conditioning in large plants, and it's also used as a foam blowing agent in insulations. And the next important refrigerant is what is known as Freon 22. Its chemical formula is CHClF2, and it's very widely used as a refrigerant in air conditioning systems. And after this, a host of refrigerants have followed by the modification of hydrocarbons. Here all these 3 freons like R11, R12 and R22, they are derived from methane. Of course, you can also have other refrigerants which are derived from, say, ethane. So one can have a large number of refrigerants basically derived from the saturated hydrocarbons. Since so many refrigerants were introduced, a numbering system was introduced to identify the refrigerants from its number. So that's the reason why, for example, Freon 12 is called as R12, and the number 1, 2 has significance, and if you follow the numbering system, you can tell what is the chemical composition by just looking at the number. So these issues I will discuss when we discuss refrigerants in a later lesson. Now let us look at how CFCs compare with the early refrigerants. Compared to the early refrigerants, CFCs are non-toxic, they are non-flammable, they are chemically stable, they are compatible with common materials, they are available for a wide refrigeration temperature range. So you can see that almost all the perceived problems of the early refrigerants were in fact eliminated by the invention of or by these new working fluids. In fact, the non-toxicity and non-flammability of these refrigerants used to be demonstrated by Thomas Midgley. What he used to do is he used to take a mouthful of the refrigerant and he used to blow it over a burning candle, and the flame used to get extinguished. That's how he used to say that it is non-toxic, because even after inhaling there is no problem, and it's non-flammable because the flame used to get extinguished. So soon these refrigerants have become very popular, and they have been used very widely because of all these favorable properties. Now let us look at the impact of CFCs. First impact is that all early refrigerants except ammonia are replaced by various CFCs. Ammonia could not be replaced because of its excellent properties. Then there is a rapid growth in refrigeration due to the safe nature of these refrigerants. And refrigeration have entered households mainly due to the invention of CFCs, and household items like refrigerators, air conditioners have become very popular all over the world. And as a result of this, the production and consumption of CFCs has increased exponentially. So you see suddenly a lot of manufacturing plants coming up manufacturing CFCs. And as I was mentioning, every company used to have their own trade name. For example, the DuPont company used to call their refrigerants under the name Freons, and the General Electric company used to call them as Genetrons. So as a result of all these favorable properties, refrigerants based on CFCs have been used very widely for almost 50 years, and everybody felt that they have finally got a safe refrigerant. But suddenly something has happened, and in 1974 two scientists, Rowland and Molina, have proposed a theory of ozone layer depletion. Their theory says that the CFCs, if they are released into the atmosphere, will lead to the depletion of ozone layer. So let us look at what is this ozone layer and how the CFCs lead to ozone layer depletion. So Earth is surrounded by a stratosphere which extends from 15 kilometers to 50 kilometers above its surface, and this stratosphere has a layer of ozone. So how this ozone is formed, let us look at the equations here. Oxygen in the ozone layer reacts with, under the action of you have the ultraviolet rays. As you know, sun emits a wide variety of radiation, and ultraviolet rays are one among them. And under the action of ultraviolet rays, oxygen molecule splits into two radicals of oxygen. This one radical of oxygen reacts with one molecule of oxygen, forming one molecule of ozone. So as a result, ultimately what we have is three molecules of oxygen react reversibly to form two molecules of ozone. So as a result of this, you have a presence of ozone in the stratosphere. This ozone layer is very important for survival of life on Earth, because as I mentioned, sun emits ultraviolet radiation, and ultraviolet radiation is harmful to life. We will see what are the harmful effects of this ultraviolet radiation, and thanks to the presence of ozone layer, we really don't get much of the ultraviolet radiation, and that is how life has evolved. That's what scientists say, that life has evolved only after the ozone layer has formed on the in the stratosphere. Now let us see what is the effect of chlorofluorocarbons. As I mentioned, one of the favorable properties or perceived favorable properties of chlorofluorocarbons is their high chemical stability. So when these chlorofluorocarbons are released into atmosphere, for example due to leakages or when you are servicing the systems, then they stay in the atmosphere for a long time. That means they don't break down or they don't dissociate into atoms. So a chlorofluorocarbon molecules stays as a chlorofluorocarbon only. And over a long period of time, due to concentration difference, the chlorofluorocarbon molecule slowly migrates to the stratosphere. Once it goes to the stratosphere, there it encounters ultraviolet radiation. So when it comes into the presence of ultraviolet radiation, dissociation of chlorofluorocarbon takes place, because UV radiation has high energy. So because of this, you can see here that, for example, one R12 molecule under the action of ultraviolet rays releases one chlorine radical, and this chlorine radical reacts with ozone and forming a chlorine monoxide, ClO, and one molecule of oxygen. And again this chlorine monoxide react with one oxygen radical, forming one molecule of oxygen and one radical of chlorine. So what has happened in this process is one mole of chlorofluorocarbon has released has destroyed one mole of ozone, and it has formed oxygen, and again it is free to react with other moles of ozone and dissociate other moles of ozone. That means a single molecule of chlorofluorocarbon is capable of dissociating several thousands of ozone molecules, as a result of which this balanced chemical reaction, or this chemical reaction which is under dynamic equilibrium and which was responsible for the presence of ozone gets disturbed. That means the chlorine atom favors the reverse reaction and there is more of oxygen and less of chlorine, as a result of which ozone holes are formed in the stratosphere. And when you have ozone holes, then you can see that they allow the UV radiation to enter through the stratosphere, and finally the UV radiation reaches the surface of the earth. So this is the theory proposed by Rowland and Molina. Initially it started as a theory. So now that is what is shown here. The CFCs are released from the earth and they slowly migrate to the stratosphere, where they dissociate the ozone molecules, and as a result in this side, the greenish side where depleted ozone layer is there, more amount of UVB radiation passes through and it reaches the earth, whereas where you do not have any hole, less amount of UVB radiation comes to the earth. So this is the principle of ozone layer depletion. And subsequently experimental studies have been carried out, and they have found that the theory proposed by Rowland and Molina is actually true, and they have discovered large ozone holes on Antarctica, for example. And it is found that not all chlorofluorocarbons are equally capable of destroying the ozone layer. So based on this observation, they started rating the chlorofluorocarbons based on what is known as ozone depletion potential, or ODP. ODP stands for ozone depleting potential, and for this they have taken R11 or CFC11 as the basis, and CFC11 has been assigned an ODP of 1, and all other refrigerants have been rated against this reference of CFC11. Now let us look at the consequence of ozone layer depletion. What happens because of ozone layer depletion? It is observed that if ozone layer depletes and ultraviolet radiation reaches earth, it leads to skin cancer, cataracts and weakened immune system, and it also destroys DNA structure. All these problems will take place in human beings, and it is also observed that this will also have adverse effect on crop yield, and it will also have adverse effect on terrestrial and aquatic ecosystems. So people have suddenly realized that this ozone layer depletion is a global problem, and it is a very serious problem. So since it is so serious, in 1987 several industrialized nations have met in Montreal, and they have proposed a protocol under which they proposed the banning of all the ozone depleting CFCs in a phase wise manner. Initially only the industrialized nations have joined this protocol, but subsequently almost all the countries of the world have ratified this protocol. As a result of this Montreal protocol, it has been agreed to ban the completely ban the use of all chlorofluorocarbon based refrigerants. And since you are banning them, you require a safe refrigerant. So again a search for safe refrigerant has started all over. In addition to the ozone layer depletion problem, there is also another environmental problem which is also related to the presence of CFCs in the atmosphere. This problem is known as global warming or greenhouse effect. Let us look at the global warming, and let me explain the principle or concept of global warming. As you know, Earth is surrounded by an atmosphere, and this atmosphere consists of several gases such as carbon dioxide, nitrogen, oxygen, water vapor, etc. And some of these gases such as carbon dioxide, nitrous oxide, or oxides of nitrogen and water vapor act as greenhouse gases. What is the meaning of greenhouse gases? As you know, solar radiation mainly consists of short wave radiation, and this atmosphere consisting of all these gases allows the short wave radiation to pass through and reach the earth. So short wave radiation from earth passes through the atmosphere and reaches the surface of the earth, and the earth's surface absorbs this radiation and its temperature increases, and the earth in return emits long wave radiation. So sun emits short wave radiation and the earth emits long wave radiation, and it is these greenhouse gases, they allow short wave radiation to enter the atmosphere, but they absorb the long wave radiation, and that's how they trap the long wave radiation, as a result of which there is trapping of heat within the atmosphere, and the equilibrium is achieved at a higher temperature. That means because of the presence of these greenhouse gases, a warm blanket develops around the earth, and this warm blanket is very essential for life on earth. And it is theoretical calculations show that if in the absence of this warm blanket, or in the absence of these greenhouse gases, the earth's temperature will be about -18 degrees centigrade, and no living being can survive at this kind of temperatures. So for us this global warming is very much essential, but unfortunately the ecosystems have developed in such a manner that they are very sensitive to the temperature of the atmosphere, and this temperature, in the absence of any other artificial additives, is just right for our survival. But because of the presence of large scale presence of CFCs, this greenhouse effect or global warming effect is getting disturbed. Okay, how this happens is, the chlorofluorocarbon, as I mentioned, during their leakage or servicing etc., are released into atmosphere, and it is observed that they are capable of absorbing much more amount of long wave radiation compared to the conventional greenhouse gases such as carbon dioxide. Now to denote the potential of these gases for absorbing long wave radiation, carbon dioxide is taken as the reference, and carbon dioxide has been given a global warming potential of 1. On this scale, it is observed that CFCs have global warming potential of several thousands. That means one molecule of CFC is equivalent to several thousand molecules of carbon dioxide. So you see that when you release lot of CFCs into atmosphere, it is equivalent to releasing a large amount of carbon dioxide into the atmosphere. So this will obviously disturb the greenhouse effect, and as a result of which more long wave radiation gets trapped in the atmosphere, leading to higher global temperatures. And as I mentioned, our ecosystems are very sensitive to temperatures, and even a temperature variation of say 1 degree can lead to several catastrophic changes. So let us see what are these problems. These are, as I mentioned, CFCs have global warming potential, which is several thousand times greater than carbon dioxide, and there is another small issue. Refrigerants contribute to global warming potential in two manners. One is in a direct manner, that means when you release chlorofluorocarbon into atmosphere, they directly start absorbing the long wave radiation, and that is how they contribute to global warming potential in a direct manner. However, they also have an indirect effect, that means all these refrigeration systems using the refrigerants consume energy, and in Vapour Compression Refrigeration Systems you have to give electrical or mechanical energy as the input, and now to produce this mechanical or electrical energy one has to burn, for example, fossil fuels. That means electrical energy requires burning of fossil fuels, and the burning of fossil fuels leads to release of carbon dioxide into the atmosphere. So these are the direct and indirect effects of chlorofluorocarbon, and the direct effect depends upon the leakage, the rate at which you are releasing the CFCs in the atmosphere, and the indirect effect depends upon the efficiency of the system. For example, if there are two systems and one system consumes less energy and the other system consumes more energy, the system consuming less energy releases less amount of carbon dioxide into atmosphere, and the system consuming more energy releases more amount of carbon dioxide into the atmosphere. So you can see that efficiency comes into picture, and ultimately the contribution to global warming increases with the inefficiency of the system. So these are the two effects, and another index called total equivalent warming index, or TEWI, has been formulated to account for both the direct and indirect effects of global warming. Now let us look at the effects of global warming on our ecosystem. It is observed that if the due to global warming, if the temperatures change, there will be unpredictable changes in weather and wind flow patterns, and this will also give rise to increased sea levels, because the higher temperatures will lead to more melting of polar ice caps. As a result, the sea levels will increase, and as you know, once the sea levels increase, there is every possibility that many of the lowland countries may get submerged. So this is a very serious problem. And the third effect is that due to the varying temperatures or due to the increased temperature, there will be a redistribution of crops and animals. So all these problems are of serious nature, as a result of which the global warming has become a very major concern for the global community. In fact, you might have read in the newspapers and all, in all these Kyoto Protocol and all, several industrialized nations again have met and they have discussed on ways and means by which the global warming gases can be reduced. That means the release of global warming gases can be reduced. Of course, in addition to CFCs, other gases also contribute to global warming potential. So the problem of global warming potential includes other aspects also. So as a result of the negative side of the CFCs with reference to their effect on ozone layer depletion and global warming effect, most of the refrigerants have to be banned. So again, you have to find some safe refrigerants, and now people have become wise, and for them now the safety doesn't mean a personal safety only, but it's also environmental safety. So the new refrigerants must be environment friendly, and they also must be energy efficient. So what are the requirements in the context of Montreal Protocol and subsequent protocols? So for any refrigerant which should be a replacement for CFCs has to be a non-ozone depleting. That means it should be a non-ozone depleting substance, and its ozone depleting potential must be 0, and it should have as low global warming potential as possible. People have again found several synthetic refrigerants which meet these criteria. Okay, synthetic refrigerant, there are several synthetic refrigerants which have 0 ODP, but they have some GWP. And people have also again looked at the natural refrigerants which were used earlier and which were phased out due to some problem or other. So right now you have some non-ozone depleting synthetic refrigerants and also natural refrigerants which have 0 ozone depleting potential. And some of the early refrigerants, as I was mentioning, such as carbon dioxide and hydrocarbons which were phased out, are they again coming back because of their favorable effect on the environment. This table shows a brief look at alternatives vis-a-vis applications. For example, in domestic refrigerators, previously CFC12 was used as a refrigerant, and CFC12 has a ozone depleting potential of 1, so it had to go. So in its place, now refrigerants such as HFC 134A and hydrocarbons are being proposed. These two are non-ozone depleting substances and they have reasonably low global warming potential. And for the air conditioning application, previously CFC 11 was used, CFC 12 was used, and HCFC 22 was used. Now these CFC refrigerants are being replaced with HFC 134A. It is HFC stands for hydrofluorocarbon, and HC stands for hydrocarbons, carbon dioxide and the mixers. So these are the new refrigerants which are being suggested in place of the older refrigerants for air conditioning applications. And in cold storages, previously HCFC 22, that is a hydrochlorofluorocarbon 22 was used, and a mixer R502 was also used, and these two substances have non-zero ozone depleting potential, so they also have got to be banned. And so they are now being replaced by ammonia and hydrofluorocarbon mixer. And in for heating applications in heat pumps, previously CFC 114 and CFC 11 were used, and both these are ozone depleting substances, so they are being replaced by hydrocarbons and water. So this is just a brief look at the possible alternatives to the CFC refrigerants, and most of the CFC refrigerants such as CFC 11, CFC 12 have already been banned, whereas refrigerants such as HCFC 22, since it has a very low ozone depleting potential, people have felt that we can use it for a little longer. That means you can use it up to say 2020, and that means it has to go in 2020. So this is a brief look at the development of refrigerants and how we have made a full circle, starting with natural refrigerants, and again we are coming back to natural refrigerants. Now let us look at another very important aspect of compressor development and a brief history of compressor developments. Compressor is the most important and is the most critical component of any vapor compression refrigerant system. In fact, it is called as the heart of a vapor compression refrigerant system. This is because it is always the most, it is the major cost component of any vapor compression refrigerant system. Typically 30 to 40% of the total plant cost is due to the compressor. So obviously it is very important that you select the right compressor, and it has a great influence on energy consumption, reliability and serviceability of the system. So, selection of suitable compressor is another important step apart from the selection of suitable refrigerant. Now, compressor types. There are a wide variety of compressors. Let us look at these different types of compressors. Compressors can be classified into positive displacement type compressors. In positive displacement type compressors, compression is achieved by trapping certain amount of a refrigerant or a gas in an enclosed space. So, first you trap some amount of refrigerant in an enclosed space and then you reduce the volume. So, as you reduce the volume of a fixed mass of gas, its pressure rises. So, you raise the pressure till the pressure exceeds or equals that of the condenser pressure. So, this is the principle of positive displacement type of compressors. And again, under positive displacement of type of compressor, we have several types. For example, reciprocating compressor, rotary compressor, screw type of a compressor, scroll compressor. Apart from that, there are also other types of compressors like trochoidal compressors and all, which are relatively new. So, reciprocating, rotary, screw and scroll are the most important types of positive displacement type of a compressor. The other type of compressor is known as rotodynamic type of compressor. In all positive displacement type compressors, on a microscopic level the flow is not steady. In fact, the flow is pulsating. This leads to actually vibrations because of the pulsations. However, on a macroscopic level, due to the high speed, you do not really feel that the flow is pulsating. Okay, if you put a mass flow meter which gives you the macroscopic flow rate, you cannot really detect the pulsations, but if you put a very sensitive flow meter, then you find that the flow is pulsating. The other type of compressor, that is rotodynamic type of a compressor, is a steady flow device, and in these compressors the compression is achieved due to the exchange of angular momentum between a high speed rotating mechanical element and a steady fluid flowing through the element. So, this is the principle of rotodynamic compressor. That means you impart angular momentum to a steadily flowing fluid and then convert this angular momentum to pressure. And the two important types of rotodynamic compressors are centrifugal type and axial flow type. Centrifugal types are also known as turbo compressors, and they are widely used in large refrigeration capacity systems. Now, let us look at reciprocating compressor. A reciprocating compressor is called as the workhorse of refrigeration industry. That means it is the most popular among all the refrigerants, all the refrigerant compressors. So, let me explain the working principle briefly. A reciprocating compressor resembles in many ways a IC engine. So, here you have a cylinder, a piston, connecting rod and a crankshaft, and you have a discharge valve here and a suction valve here. As this crankshaft rotates in this manner, the piston slides in the cylinder. So, piston reciprocates in the cylinder as the crankshaft rotates. So, you are converting basically the rotating motion of a crankshaft into a reciprocating motion. That is why you call it as a reciprocating compressor. Now, as I was mentioning, this is a positive displacement type of a compressor. So, you have to have an enclosed space and you reduce the volume of the enclosed space. So, here the enclosed space is formed due to the presence of the cylinder, the piston and the two valves. When the two valves are closed, then you have an enclosed space here. Okay, so, if you trap some amount of gas here and you reduce the volume by moving the piston in this direction, then the volume reduces and pressure builds up. So, the working principle is like this. Let us assume that initially the compressor is at the inner dead center. That means it is at this position. The piston is at this position, and as the crankshaft rotates, the piston moves towards the outer dead center or ODC. So, as the piston moves towards the outer dead center, there will be expansion of the gas inside the cylinder, hence the cylinder pressure drops. When the cylinder pressure drops, due to the pressure difference between the evaporator here and the cylinder here, this suction valve opens. Once the suction valve opens, refrigerant from the evaporator flows through this inlet and enters into the cylinder. This process continues as long as the piston is moving towards the ODC. Once it reaches ODC, the further rotation of crankshaft leads to the movement of piston in the reverse direction. That means now the piston will start moving from the outer dead center to the inner dead center, that means in this direction. When it starts moving in this direction, the pressure starts rising because the volume gets reduced. As this pressure exceeds that of the evaporator pressure, suction valve closes and discharge valve is closed now. At this moment discharge valve is closed. So, both suction and discharge valves are closed, and as the piston moves, the volume reduces, pressure builds up. Once this pressure exceeds the pressure of the condenser, that means the pressure at this point, this is the condenser pressure, then the discharge valve opens. So, once the discharge valve opens, the refrigerant that is trapped inside this enclosed space escapes through this discharge valve, goes to the condenser, gets condensed, and then it flows through the expansion valve, goes to the evaporator, and the cycle is completed. So, that means the movement of the piston inside the cylinder will give rise to suction and compression, and as you can see that flow is not steady. That means at some moment during at some point refrigerant enters, and at some point it gets compressed, and at some point it gets discharged. So, if you put a very fine probe here, then you find that the flow is pulsating. Okay, so this is the basic principle of any reciprocating type of a compressor. So, now let us look at the development developmental issues regarding the reciprocating type of a compressor. P. N. Russell began the manufacture of the first vertical two-cylinder compressor in 1859. So, this is the first commercialization of compressors, and as the name implies, it is vertical and it had two cylinders. And Charles Tellier has developed a horizontal single-cylinder compressor in 1863. And T.S. Lowe has developed carbon dioxide compressor in 1868. And Raoul Pictet has developed horizontal oil-free sulfur dioxide compressor in 1874, and Linde has introduced horizontal double-acting compressor in 1877. So, this shows a picture of Linde's compressor. Why I am showing this is one of the landmark events in the history of refrigeration, and this shows the horizontal double-acting compressor with a stuffing box. Now, let us look at the early compressors. What are the characteristics of the early compressors? The earliest compressor is a hand operated compressor. Now, you can see that if you want to run the compressor, you have to supply some mechanical energy. That means some drive is required to run the compressor, and the first compressor, the drive was provided by a human being. That means it was a hand operated compressor, it's just like our normal water bore wells. And later the hand operated compressors were replaced with steam engine driven compressors. This happened sometime in 1850s. And the early compressors were essentially open type. Open type means the body of the compressor and the driving mechanism. For example, if it is steam engine, then the steam engine and the compressor were separated. So, this is what is known as a open type of a compressor. And they were typically very low speed compressors. That means the speed used to be about 50 rpm. And their size used to be very large. For example, they used to have diameters as large as 0.5 meters, and the stroke length used to be as large as 1.2 meters. And since the speed is low and the size is large, typically they used to have small clearance. What will be the effect of this clearance and all, we will discuss when we discuss the performance of reciprocating compressors. But for the time being, let me say that the early compressors used to have small clearance, and they also used to have large valves. As a result of this low speed and large valves, they were able to handle a mixture of liquid and vapor. So, early compressors were handling refrigerant liquid plus vapor mixers. Now, let us look at some of the important landmarks. In 1897, a Belgian scientist, John Lebrun, has introduced a rotary stuffing box to reduce leakage. Now, one of the problems with open type of compressor is that the driving shaft goes into the body of the compressor. So, where it enters into the body of the compressor, you must provide some kind of a sealing so that it can rotate freely. At the same time, refrigerant leakage is minimized. So this is a typical problem with any open type compressor. Because of this particular arrangement, there will always be some leakage of refrigerant near the shaft. So people have tried different types of seals to minimize the leakage. It is not possible to prevent the leakage completely, but you can minimize the leakage. So first breakthrough happened when Lebrun has introduced a rotary stuffing box. Using a rotary stuffing box, you can reduce the refrigerant leakage to a large extent. Then gradually the steam engine driven compressors were replaced with electrical motor driven compressors. This is a truly landmark event or very important event in the development of compressors, because once you use the electrical motors for running the compressors, it offers many advantages. You can have speed, and you can have compact design, and many other important advantages. And this happened sometime in then high speed compressors, that means speeds above 500 rpm were introduced in 1920s. Let us look at what is the effect of speed. Let me show the effect of speed here. This table shows the effect of compressor speed. For example, in 1910 we had a ammonia based compressor which had 2 cylinders and which was running at 70 rpm speed, and it was giving a cooling capacity of 6.5 kilocalorie per hour per kg of the weight of the compressor. And in 1940 the compressors, ammonia compressors, used to have 4 cylinders and the speed used to be 400 rpm. So now you can see that the cooling capacity per kg of the compressor weight has increased from 6.5 to 42 due to the increase in the speed and also in the due to increase in the number of cylinders. Whereas in 1975 a typical R22 compressor with 16 cylinders and with a speed of 1750 rpm was giving a cooling capacity of 200 kilocalorie per hour per kg. So you can see that there is a 2 order of magnitude improvement in the cooling capacity with the speed, the increase in speed. So if you want to really increase the speed of the if you want to make a compressor compact, one has to go for higher speeds, and all this has become possible due to the use of electrical motors and multi-cylinder arrangement. Now let us see what are the other important landmarks. A hermetic compressor, which is again a very important landmark in the development of compressors, was introduced in 1918. Now let us see what is a hermetic compressor. As I was mentioning, in a open type of a compressor you always have a problem of refrigerant leakage, because the compressor and the motor, for example, are placed widely apart and the rotating shaft has to pass through the body of the compressor where the leakage takes place. Now if you have a leakage in a system, a continuous refrigerant leakage from the system, then after some time its performance gets affected. So what is done in systems using open type compressor is that you have to provide a large refrigerant storage which will take care of the leakage to some extent, but after certain time you have to recharge the refrigerant into the system. That means all open type of compressors require periodic maintenance. Obviously periodic maintenance is not possible if you are planning to use these compressors in say domestic refrigerators. You cannot have regular maintenance in your house. So people felt that this problem of open type of a compressor has to be eliminated. So this led to the development of a hermetic compressor. So you can see the photograph of a hermetic compressor here. In a hermetic compressor, both the motor and the compressor are housed in the same external housing. That means both are mounted in an external shell. As a result, any refrigerant leakage from the compressor is confined within the shell, and to this shell are attached the suction and discharge lines through a permanent welding or brazing process. As a result, the leakage of refrigerant is completely eliminated. So because of this important advantage, hermetic compressors have become very important for the development of domestic refrigerators and small compressors, small air conditioners, etc. Of course, one of the problems with hermetic compressor is that since you are keeping the motor also inside the refrigerant system, the heat losses because of the inefficiency of the motor becomes a load on the refrigerant system. As a result, hermetic compressors are less efficient compared to open type of a compressor. So normally you use hermetic compressors in small systems where efficiency is not so important, and use open type compressors in large systems where efficiency is important. Now let us look at other types of positive displacement type of compressors. One of the major problems with the reciprocating compressor is that you are converting a rotary motion into a reciprocating motion. This will give rise to vibrations and higher noise. As a result, people have tried to use the positive displacement machines where you do not have to convert rotary motion into reciprocating motion, and several of these machines have been invented and they have been used in refrigeration industry. The first diaphragm type of a compressor was patented in 1919 in France, and a rotary vane and rolling piston type of compressors entered in the market in 1920. I will not explain the working principle of these compressors because we will be discussing these when we discuss compressors, but I will just show the schematic of a rotary compressor. A rotary vane, this picture shows the schematic of a rotary vane type of a compressor, and here we have the cylinder here and a rotor, and it consists of different number of vanes. For example, this particular type here consists of 4 number of vanes which are freely supported or spring loaded and which are kept in the slots cut in this rotor. So this is the rotor, and the shaft which rotates is mounted on the rotor, and the axis of rotation of the shaft is in line with the center of the rotor, but it is eccentric with reference to the this outer cylinder. So as a result of this eccentricity, when this rotor rotates in this direction, it creates suction and discharge effect within the compressor. So this is the principle of rotating vane type of a compressor, and it is mainly used in small refrigeration systems, and I will discuss the performance aspects and detailed working principle in a subsequent lesson. And this picture shows the schematic of a rolling piston compressor. And another very important type of a compressor called a screw compressor was invented in 1934 by Lishom in Sweden. This picture here shows the photograph of a hermetic screw type of a compressor. As you can see here, a screw compressor uses a helical screw and a mating component, and the rotation of these helical screw and the mating components gives rise to suction and compression effects. Then the scroll type of compressor are commercialized in 1980s. Scroll type of compressors are used in small refrigeration systems, and this picture here shows a small hermetic scroll type of a compressor. Now let us briefly look at centrifugal compressor. As I mentioned, a centrifugal compressor comes under the rotodynamic type, and it was first conceptualized by Auguste Ratou of France in 1890. And let me show the schematic of a centrifugal compressor. This shows the schematic of a centrifugal compressor. You have a fast rotating, this will be rotating in this direction or in the opposite direction. This is called as the impeller here, and the gas enters through this inlet casing and it fills the space between the impeller blades. So as the impeller rotates at high speed, it imparts angular momentum to the gas. That means the gas gains the angular momentum, and the gas is thrown out because of the centrifugal action, and it enters into this vaneless diffuser. And in the vaneless diffuser, some part of the kinetic energy is converted into pressure, and from this vaneless diffuser it enters into the outer volute casing, and as you can see, the cross sectional area of the outer volute casing gradually increases. As a result, the kinetic energy of the fluid is converted into pressure. So ultimately a high pressure gas comes out of the outlet. So, this is the basic working principle of a centrifugal compressor, and it is a steady flow device, as I have already mentioned. That means you get a steady stream of fluid outside out of the compressor. And the one advantage of this type of a compressor is that since it is a steady flow machine, you do not have many vibrations like what you see in reciprocating type of a compressor. As I mentioned, this was conceptualized in 1890, and in 1920s this was actually perfected by Willis Carrier in USA, and he used these compressors for air conditioning applications to start with. Nowadays, of course, these are also used in large refrigeration plants also, and there was a rapid growth of these compressors in 1930s with the invention of CFCs. Currently, they are used for a wide variety of applications with a wide variety of refrigerants mainly in large capacity plants. Now, let us just look at a brief comparison between centrifugal versus reciprocating type of compressors. Compared to reciprocating type, centrifugal compressors are compact for large capacity systems, refrigerant flow is steady, there is less vibration and wear, and compared to reciprocating compressors, centrifugal compressors, reciprocating compressors are simpler in construction and they are rugged, and they offer good part load performance. So, as a result, you find that in refrigeration industry a wide variety of compressors are used for different applications. When you want small capacity, you normally use a reciprocating compressor or other positive type of displacement compressors. When you want very large refrigeration capacity, one generally uses a centrifugal compressor because it is more efficient and more compact for large capacities, and screw compressor comes in between reciprocating and centrifugal. So, almost all types of compressors are used in refrigeration industry for different types of applications. So, this is a brief history of refrigerant and compressor development. Now, let us conclude. Let us see what are the conclusions based on this lesson. We have seen that vapor compression refrigerant technology has achieved a high level of maturity mainly due to development of a large number of refrigerants and development of a large variety of efficient compressors for various applications. Currently, the efforts are on to develop eco-friendly refrigerants in the view of ozone layer depletion and global warming effects. The focus is on eco-friendly refrigerants for different applications, and the development of more energy efficient, compact, reliable and quiet compressors. There are also other types of compressors such as the linear piston type, trochoidal type, acoustic type compressors. These are being developed and they are still at various levels of development, and they have certain advantages compared to the conventional refrigerants, but these are, as I said, they have not yet been commercialized. So, now I will give you some questions based on this lesson, and the answers for these will be provided in the next lesson. Thank you.